Okay, the final section of this chapter is going to be on chi-squared analysis. So chi-square analysis evaluates the influence of chance on genetic data and it provides us with a test to determine if observed data is consistent with expected results. And so this is, a simple case of there's uncertainty when you have a limited sample. So if you roll a die, you expect there's to be some uncertainty in terms of the numbers that are returned. And so you want to have some sort of test to say, is this die completely random or is this die loaded to favor certain numbers when it's rolled? And so, we covered this before the results of Mendel, and we had both actual results that he received, and then we also had kind of this expected results. So the ratio of all of these crosses we kind of asserted to be 3 to 1. But if we actually calculate the ratio, we find that they're not exactly the same. So 2.96 to 1, 3.01 to 1, and so on and so forth. And so the question is does this data actually match what would be expected from a 3 to 1 ratio, or are these numbers actually significantly different? And so maybe something is going on where this actually indicates that kind of our model of how genetics works is completely wrong, and that the ratio is 2.84 to 1. So maybe there's not independent assortment between different chromosomes. Maybe some combinations are less likely to occur, but it's just in like some sort of like subtle fashion. And so how do we distinguish between these? How do we know if this number right here is consistent with our expected number? And so the idea is that you have data and you have expectation, and that's what you're trying to match together. So when we compare these data, so we always have to accept the fact that there's random fluctuations that occur due to chance. So independent assortment, just just which gametes are actually used for fertilization. When Mendel did all of his experiments, there is a set where chance occurs, and so you can have fluctuations. But there's also this idea that sample size matters. So the more times you do an experiment, the more times you would expect it to get closer and closer to the expected ratio. So what does that mean? So if Mendel did his experiment 10 times, 100 times, 1,000 times, or 10,000 times, the ratio should get closer and closer to 3 to 1. So we might not be surprised if the ratio is 1 to 1 in this situation, just because it was only done 10 times, and chance plays a much more important role. But in this case, we expect it to be, pretty close to 2.99, let's say 2.99 to 1. We expect it to be pretty close to 3 to 1. And that's just the sense the more you do things, the less important random fluctuation there is. And so the chi-square test is a pretty straightforward test that allows us to test this. And so the null hypothesis that you set up assumed that the data fits your expected ratio. And so our expected ratio is 3 to 1. And so now we want to say, do these deviations from the ratio of 3 to 1, do those fall within the bounds that we would expect, or does there appear to be a significant difference? So the apparent difference just can be attributed purely to chance. And so the chi-square is the goodness of fit to that null hypothesis. So the null hypothesis is our expected ratio is correct, and now we compare the data to that. And so this is where we have to worry about observed versus expected. So the expected, again, is the 3 to 1 ratio. The observed is simply, the actual data that comes out. So this right here is the observed data. So how do you do a chi-square analysis? So first you kind of want to talk about your expected ratios. And so you can actually show, we're going to show you how to do this on both a monohybrid and a dihybrid cross. So in this case, you have, for the monohybrid cross, just you have two different phenotypes. For example, tall versus dwarf. And you have the expected ratio of 3 to 1. So 3/4 of the offspring you expect to have one phenotype and 1/4 the other. And so now let's say we have done this cross and we have generated a total of 1,000 plants, and we find that 740 of them are tall and 260 of them are short. So these are observed phenotypes that we see. So now we can calculate the expected number that we would have. So we take this expected ratio, which is 3/4, and so if we multiply 3/4 times 1,000, what we expected to see was 750 tall plants, and we expected to see 250 short plants. So just as a reminder, this line is tall, and this line is short. And so now we see that there's a deviation between what we observed and what we had expected. So in one case, there's 10 more than expected, and the other case there is 10 less than expected. So there's 10 more short plants than expected, and there's 10 more tall plants that are effective. And so we just need to calculate that number for both, so negative and positive 10. And then what you do is you actually square that deviation. So we take that negative 10 and square it, and we get 100. And then we square that positive 10 and get 100. And then finally, we normalize this by dividing by the expected number that we thought we would get. And so if we take the expected number here, 750, we take the 100 divided by 750, and we get this number 0.13. So 100 divided by 750, and then in this case we do 100 divided by 250 because we expected to get 250 short. And so now we add this up, and we get our chi-squared value of 0.53. So this gets converted to a probability, and the way you convert the chi-squared value to a probability is very confusing at first, and we will get to that in the next slide. So in this slide, I basically showed you how to calculate the chi-squared value using your expected versus observed classes, and then just for now, we'll just take it at face value that we're able to convert this number into a probability. And so this means that there's a 0.48 probability that these observed ratios could be produced by our expected ratios. And so this is good. This means that they are consistent with each other. If it was less than 0.5, then we would reject then the chi-test would reject the null hypothesis, which would mean that the observed ratios do not match the expected 3 to 1 ratio. So we can also do this with a dihybrid cross. So let's say, yellow smooth, yellow wrinkled, green smooth, or green wrinkled. So all we're doing right here is taking the dihybrid cross that we covered between the yellow seeds and the smooth shape. So the yellow smooth is dominant and most common. The green wrinkled is recessive and the least common, and so the expected ratios is 9 to 3 to 3 to 1. And so if we do a cross in this situation, then we expect to see, and in this case they've looked at 1,008 pea plants. We can just multiply these ratios times 1,008 to get the 4 expected values that we see. So if we did this cross and looked at 1,008 animals, 1,008 plants, 567 we would expect to be yellow and smooth, 189 would be yellow wrinkled, 189 would be green smooth, and then 63 would be green wrinkled. And so in this case we did this, and now we have data, and so the data is the following. 587 were actually yellow smooth, and then so on and so forth for the other 4 categories. So in this first case we have 2 categories, and in this case we have 4 categories. And that's just because we're looking at a monohybrid versus a dihybrid cross. Again, you calculate the deviation just as you did before by subtracting the observed from the expected. You then square that deviation to get those 4 values, and then you divide by the expected values. So in this case, our chi-squared value is 4.16, so this number is higher, and so that results in a probability of 0.26. So calculating chi-squared hopefully is very straightforward for you. So calculating this value, it's very clear how you would do it, but we haven't covered at all how we convert this chi-squared value into a p-value. So in both of these cases, just as a reminder, we say that the observed results are consistent with our expected ratios. And so in order to translate this, it's important to know the degrees of freedom for your distribution. And so that is simply the number of categories minus 1. And so in this monohybrid cross, there was 2 categories. There was 2 phenotypes, tall and short. And so the degrees of freedom is 2 minus 1 equals 1. So there's 1 degree of freedom for this test. And then in the second category, there was a total of 4 different phenotypes. And so 4 minus 1, so the degrees of freedom for the second dihybrid chi-squared test is 3. So that's the first thing that you need to do. You need to calculate the degrees of freedom for your particular test. And then you typically use this table. And this table tells you how to translate your chi-squared value into a range. And so, just as a reminder, the first thing that we calculated, the chi-squared value was 0.53. And so you can either do this graphically or you can do this using a table. So you take this chi-squared value, which is approximately right here on the x-axis. So the x-axis shows chi-squared values. And you go up until you reach the point of your the line that corresponds to your number of degrees of freedom. And so for this first case, that is 1 right here. And so you can simply just follow this line over here to identify the p-value, which is listed on the y, and that's equal to 0.48. So let's do this now for the second case, the dihybrid test. So that's 4.16. So that starts something like right here. And so now in this case, we go up until we reach this line right here. So we started with the chi-square value of 4.16, and now because the dihybrid test has 3 degrees of freedom, we move up until we reach this line, and now we go across to calculate the probability. So in this case, it's probably a little bit above 0.2, and that matches 0.26. So I apologize, my lines aren't exactly straight. You can also calculate this using a table. So in this case, the chi-squared value is 0.53. And so this just allows you a range. So we know that 0.53 falls within 0.46 and 1.64. And so this tells us that the probability is somewhere in between 0.25 and 0.25, which agrees with that. For the second case, the chi-squared value is 4.16. But the degrees of freedom are 3 degrees of freedom, so we just simply need to look at this line right here. And so that again tells us that the probability falls in between 0.2 and 0.5, which agrees with our result. So if you want a chi-squared value that allows us to say the ratios are different, we basically need to be in this aspect of the table. So this is where 0.05 is a common statistic value that you use to say that you reject the null hypothesis, and this is set by statisticians. And so if you have a monohybrid chi-squared test where your chi-squared value is 3.84 or greater, then you would say that this does not meet the expected value. For the dihybrid test, you need to have a chi-squared value that's 7.82 or above. You can move on further to do a tri-hybrid cross. In that case, there would be 8 total phenotypes, and so then your degrees of freedom would be 7, and then you'd be looking at this category right here. So this test is important not only if you want to do any sort of actual experimental data, it's important to know how to compare your actual data to your expected results. But it's also, we're going to see in the latter chapters that there are situations where this is violated. And so there are situations where independent assortment does not hold true, and we see a distortion in the ratios that come out. So chi-squared distribution, I know it's hard. I know it's kind of unintuitive, especially the first time you do it, but it's important that you really understand this. So please just make sure that you go through this a couple times if it's still unclear. Okay, and that's it for Chapter 3, and thank you for your attention.